Dear colleagues, your attention is invited to a presentation on the topic Intelligent Control of Industrial Compensating Devices Based on the Applications of Fuzzy Logic. The authors of the presentation Andrey Kupin, Yurii Sherstnov, Yurii Osadchuk, and Olexander Savytskyi, Kryvyi National University, Ukraine, Kryvyi. Contents. First, introduction. Second, control algorithm for compensating devices and its implementation based on fuzzy. Third, research of the effectiveness of proposed methods. Fourth, conclusion. First, introduction. Modern electricity consumers at the mining and metallurgical complex stations often have non-linear load characteristics. The presence of semiconductor converters in them and other areas of enterprise leads to a deterioration in the quality of power supply due to emergence of higher harmonic components of voltage and current, as well as other indicators. As a result, the equipment wears out faster and electricity costs might increase due to additional payment for reactive power. Thus, the network operator is forced to implement measures to compensate for reactive power. However, due to uncertainty of load and disturbances, compensating systems require more complex approaches to implementations at the design stage. A system based on fuzzy logic can implement such control. Second, control algorithm for compensating devices and its implementation based on fuzzy. An effective solution in the case of powerful consumers with non-linear loads on the network is the installation of filter compensation devices (FCDs). The main goal of FCD implementations is to reduce the harmonic compositions and control the load tangents of the object at the level of tangent phi less than 2500. Typically, powerful enterprises have a synchronous motor in their assets which can also be involved in the reactive power compensations process. The level of reactive power generations is determined by changing the execution current. On Figure 1, IX Automatic Execution Control Systems. SDRPCS Systems of Automatic Control of Reactive Power. SAS FCD Automatic System Control Stages of the FCD. The process control scheme for reactive power compensations can be implemented using the algorithm shown in Figure 2. It should be noted that the algorithm first analyzes the compensating power of capacitor installations, as losses in kW per kV ampere reactive for capacitor banks typically range from 2000 to 45 10,000, whereas for synchronous motor this value is 13,000 kW per kV ampere reactive for our conditions and existence parameters, consistent with overall evolution trend. Therefore, the most favorable compensations process is the involvement of capacitor installations in the first place. Algorithm operations descriptions. Reactive power level Q and harmonic compositions are measured or set. Check if there are fundamental reactive power. If yes, one stage is used to compensate for the harmonic components of voltage and current. If there are need for a second stage, the reactive power module is used. Checking the sufficiency of compensations of the first stage is carried out. If the level of reactive power consumption is higher, we activate the first stage. In case it is not enough, we check the activations of the second stage, and so on. If the activations of the next stage leads to overcompensations, we involve synchronous motor in the compensations process. The availability and possibility of synchronous motor for compensations is checked. It is disturbed between the synchronous motor involved in the compensation. Third, research of the effectiveness of proposed methods. Automatic control reactive power and controllers based on fuzzy logic can be used for controlling the reactive power compensations process. However, they have some difference in usage and operating principles. ACRP have built-in precise algorithms that provide automatic switching on and off capacitor depending on the level of reactive power in the electrical network. ACRP can also switch capacitor on and off depending on the voltage and current level in the network to ensure optimal reactive power compensations. Fuzzy controller allow for a wide range of factors that affect the compensations process to be taken into account, such as state of the network, the level of harmonics, the instability of the power supply, and so on. This provides a more flexible and effective management of reactive power compensations. Figure on the slide shows the main advantages and disadvantages of conventional ACRP and fuzzy logic based controllers. The main feature and the same time advantage of this system is: first, fuzzy controller allows working with fuzzy input data, which is useful when dealing with complex systems, for example, as in our case, substations with a large number of electricity consumers. Second, the use and configurations of controller based on fuzzy logic is more intuitive and simple to set up based on expert rules. After analyzing the data for the winter and summer months, the necessary base level of compensating ability was determined to be a 7,500 kV ampere hour. Since the level of reactive power consumption below this value is not normal, this only occurs in the case of disconnecting powerful consumers. For example, one of the lines consumptions of the or beneficiation plant 1. After that, the consumption of reactive power was calculated taking into account the base level. To determine the rational capacitor of capacitor bank allow of normal distributions was completed. See figure on the slide. On the graph, it can be seen that the maximum for January corresponds to 750 kV ampere hour. The highest common point is 1,500 kV ampere hour. At the third is 2,250 kV ampere hour. Thus, the level of reactive power consumptions can be determined as input parameters for the fuzzy controller. To investigate the effectiveness of fuzzy control compensating devices, the following steps will be taken. First, create and configure a fuzzy controller that will make decisions about compensating reactive power based on input data about the state of the electrical network. Second, evaluate the effectiveness of reactive power compensations with fuzzy control based on experimental data on daily power consumptions. The calculating of the fuzzy regulator will be carried out using the fuzzy logic toolbox MATLAB package. To do this, we will select input parameters that affect the compensating ability of the fuzzy controllers, as shown in figure 5. First, there is parameter of reactive power consumptions with level of consumption being low, medium and high. The second parameter is tangent phi. The next parameter is the number of synchronous motors in the network, as well as the temperature and load of the motors. These three parameters have a significant impact of the amount that we can compensate using synchronous motor. However, when a synchronous motor is highly loaded, its temperature is usually higher than normal. This is because as the load of the motor increases, its power loss from resistance caused by losses in the stator and rotor as well as losses due to magnetization increases. This leads to an increase in the motor temperature. If the motor's temperature remains low under high load, this might be a sign of ineffective operations on an emergency state. Therefore, it is advisable to combine the load and temperature parameters. On figure 7 can observe relatively low compensation values within the range consumption reactive power from 0 to 1,500 kV ampere hour and tangent phi from 0 to 1. This can be explained by the fact that there is no need for significant levels of compensations in this zone. Accordingly, starting from 1,500 kV ampere hour, the need for compensations increases. This is also important to prevent the activations of higher compensation level until such a need arises. Such a decision helps to avoid excessive reactive power generation. Figure 8 shows that for low values of the number of motors, high values of temperature relative to the normal value and high loading, the values of compensations possible are low. This can be explained by the fact that further increase in reactive power generation from this motor can lead to overheating. Therefore, in the presence of a large number of synchronous motors, we can distribute higher values of generations even at higher temperatures and loading. As seen in slide 11, according to the algorithm, the generated power using capacitor bank does not exceed the consumption power. 3 levels were used during the day in January. A constant compensation level at a 7,500 kV ampere hour and 1 levels at 750 kV ampere hour. And reactive power compensation using capacitor bank and synchronous motor and YUN. During summer days, 3 level at 750 kV ampere hour and constant level and 7,500 kV ampere hour were used. The remaining reactive power is compensated by synchronous motor. 4. Conclusion. Based on statistical data on reactive power consumption of the reactive substations and PGSC Nord map, a method for selecting the power of compensating devices to ensure minimum payment for reactive power by the enterprise has been proposed. The proposed system of automatic control of compensating devices by switching FCDs and regulation of execution of synchronous motor for reactive power compensations balances the flow of reactive power between consumers, asynchronous motor and transformers etc. with control of technological parameters of synchronous motors. The development algorithm is implemented based on fuzzy logic with the considerations of important technological parameters. The obtained level of compensating possibilities depends on all the considered parameters. According to the results of graphical representations, the required level of compensating ensures high energy effectivity. Thank you for your attention.